Okay, so thank you for the introduction and thank you very much for the invitation. It's really a great honor for me to speak in this special conference in memory of Jan Negovash. So Jan really impacted me both very deeply in mathematics and in life. So Jan has two Chinese students, and one is my best friend and the other one is my worst friend. So, and so then. And also, I attended the elliptical course of Jan when I first came to France. Sorry, I didn't remember who were my classmates, but I do remember that during the first lecture of his course, so he wrote down a program on the blackboard. And the master course at JUSU lasts for 6 weeks, and Jan finished half of the program in the first 5 weeks, and the other half in the last week. So that was really a crazy and very impressive week. So I will do the same thing today. I will finish half of my talk in the first 15 minutes, and the other half in the last 10 minutes. So now I first write down the program. So part 1 is about, so I will talk about this conjecture, period relations, and part 2 is the proof. Okay. So first, let me introduce this our situation. So 1.1 introduction. So we need to consider some unitary group, and for simplicity, I only consider the case for quadratic imaginary field. It can be CM field in general, but the notation will be very horrible. So K to be quadratic imaginary field, or in general can be CM. And I fixed an embedding from K to C, so I consider K as a subfield of complex numbers. And I take V an n-dimensional Hermitian space with respect to this quadratic extension K over Q. And I look at the unitary group attached to this Hermitian space. So it's the algebraic group over Q. So in general, an automorphic period is the Peter-Anderson product of an arithmetic or a rational vector, a rational form of itself. So we should first define what is a rational form inside a representation of U. So let me assume this small pi. So to get an algebraic structure of pi, we need to assume some conditions here. We need pi to be tempered. So we want to isolate pi from certain cohomological space. And of course, we want it to be cohomological, which means that the algebra cohomology of pi infinity with coefficients when twisted by a finite dimensional algebraic representation of U is non-zero. And we want to take the Petersson inner product of our form itself, so I assume pi is globally square integrable. Automorphic representation of U at Q. Okay, and for such representation, it's we can isolate this pi from certain cohomological space with coefficient, the coherent cohomological space of a Shimura variety with coefficients in an automorphic vector bundle. And in particular, this pi will inherit a rational structure from this cohomological space. So the rational structure. And here, what I called in my previous paper with Harold and Grobner, we call this cute cohomology. So cute from the cute cohomological space, and in some paper of regular RAM, it was called strongly inner. So the cute cohomology space is the subspace of the inner cohomology, where here Q means cuspidal and T means tempered. So the cuspidal tempered. Cohomology of unitary Shimura varieties. So it will be over a number field. I will not precise the number field, just write it down as a number field. Okay, And for such pi, we can define so-called automorphic period. I write it as q pi u. So later we'll let this pi vary and u vary, so I'll precise this u here. Just by taking any rational element inside pi for any phi in pi rational or algebraic. And so by Shimura's lemma, you can show that this one does not depend on the choice of phi up to, so it's well defined up to e, maybe I precise this number field e pi, so up to e pi multiplication. So now it comes a very natural question. So if we let this pi vary and u vary, will there be relations among these automorphic periods? So question. So if you are given a family pi I, ui related to each other, so are there relations among the periods? Before going further, I want to explain a parallel situation. So it's a more classical conjecture by Shimura. So parallel situation is like that. Okay. So if you look at the Hilbert module form, so if you have F a totally real field, if you have a quaternion algebra over F, and we want to have a family of automorphic representations of D which are related to each other, and the natural choice of this related to each other is that if they all have the same Jacques-Lens transfer to GL to AF, so then we fix, we let this transfer fix, so we fix pi Cuspidal representation of GL to AF. So let pi to be the Jacques-Lens transfer of pi to D cross if it exists. So if it exists. And it exists if pi is discrete series on these ramified places. And then we can similarly define these automorphic periods for pi. So we define q pi d again as the Petersson inner product of any phi in pi. So classically we call it arithmetic or rational algebraic if you want. So in this case, we know this phi is algebraic if and only if it takes algebraic value at CM points. So we can define it more concretely. So we have this q pi d, again it's well defined, up to, so I don't want to write down every time the number field, so just for simplicity, I write here as q bar cross. So it's well defined up to multiplication by an algebraic number. And now the question, similar question comes. So the question. So when pi d runs over the packet of Jacques-Lens correspondence, Jacques-Lens transfer of big pi, so what are their relations? we first observe a fact. So actually, this Q pi d only depends on the ramification of d at infinity. Okay, so when we talk about ramification, we can also consider the non-ramification.
What do you mean by that statement? Do you mean a fixed capital pi?
So we fix this pi represented with.
So that's fixed. So if you vary, you mean you're just varying d?
Vary d and pi. Also, when d is fixed, of course, pi is fixed. But here we vary d. Okay. So yeah, and so after this observation, we can try to label our representation simply by its non-ramification of d. So called label of pi d. So I write it as I pi d to be the say sigma, the place of f where d is ramified. It's a sigma. Okay. So then, so if we look at this label, then we can see that there's some pi d which is fundamental essential instance of the label is simple. So for this pi d, we call its periods fundamental periods, and we will try to write down the other periods in terms of these fundamental periods. So the idea is to take the unramified as minimal as possible. So for each sigma, we take the sigma Quaternion algebra, which is unramified at sigma and ramified at places outside sigma. I'll define and let pi sigma be the Jacob-Lagrange correspondence of big pi, and I define so-called fundamental periods Q sigma pi to be the automorphic periods for this pi sigma, this sigma which is unramified as minimal as possible. So to be this one. And the conjecture of Shimura, already he observed that. So it's conjecture by 77, and it's proved by Michael Harris in 1993. And I generalized this proof, so I gave another proof of this theorem in a more general setting recently. Okay, so we have this one. So this Q pi d, again, so every period is only defined up to Q by cross multiplication. So in the following, I write equality, all means that it's up to multiplication by algebraic number. So this conjecture says that in general, an automorphic period is the product of fundamental periods where you take sigma runs over the label of pi d, Q sigma pi. Okay. So this is the parallel situation. So now we go back to our situation. So we want to know the relations among this Q pi u when this pi u also runs over L packet. And so what we need to do is we first need to label our pi u, and then we should try to find some fundamental periods, and we should guess what are the relations among them, and finally we prove it. Okay. So now we look back to the unitary group case. So say a conjecture on unitary groups. So like the parallel situation, we shall fix this big pi capital. So let me first write down capital. Cohomological representation of GRN AK, and then we consider the L packet of pi by the base change. And we want this pi descends to unitary group, so a necessary condition is that this pi is conjugate self-dual. And also for the descending, we need to add a small assumption is that pi is discrete series at a inert place. So this is only in the case if n is even. So we should, in the even case, we will have an obstruction in the construction of unitary groups. So we need to assume that to make sure this pi descends to unitary groups. And now, so we have a base change from the unitary group to GRN, and so we will consider, so let's pi fixed. So we fix pi. And we shall consider this pi u, where this big pi is the base change of pi. So we consider this pi u with base change big pi. Okay. So again, we give the first observation. No facts. So the fact is that this q pi u only depends on the ur and pi infinity. Okay, so then we try to label our pi u by, so ur is only so the signature of u and pi infinity. Okay, so maybe I continue here. And now we consider, so let U be a unitary group of signature n minus SS. So we give the first label S. Okay. And once U is fixed, we look at the descending of pi. So pi infinity, it descends to, so we know exactly what's descending, and the number of its descending. It descends to n choose S in equivalent discrete series representations. And this, we know the classification of discrete series representations, they are classified by the so-called Harish-Chandra parameter. So these representations are distinguished by the Harish-Chandra parameter. And in this case, we can relate directly the Harish-Chandra parameter with this minimal k-type. So namely, whenever you have this pi infinity on this unitary group, and we have a maximal compact subgroup of this unitary group, it's just un minus s times us, we look at the restriction of pi infinity on this maximal compact subgroup. And so they will have several isotypic components, and among them you consider the one whose highest weight is shortest, and then you will get this minimal k-type here. And more precisely, let me write down this parameter explicitly. So we know our this big representation pi. So it's the classification of the admissible representation of GRNC. It will be of the form inducted from this Fourier subgroup to GRNC of some characters. And since our pi is conjugate self-dual, so the characters are of the form z1 to the power a1 and z1 bar to the power minus a1, tensor, etc. And here they are algebraic, so each AI, they are integers or half integers depending on the parity of n. And we can always arrange it in the form, the descending order. Okay, so I need them to be cohomological, so each AI, they are different. Okay, it's a regular representation. Then for each, so the descending of pi infinity then has Harshchandra parameter of the form. So just to reorder this AI, but you split it into two parts. So AI1 to AI n minus s. Oh, I use J here. And then AI1 to AI s. And this is a commutation of AI. And you see exactly there exists and choose as different parameter here. So you have this number corresponds here. And then we just label our representation pi u, so label. So once you have a descending, so with space change big pi, so I call it I again, I pi u. You just take this I1 to IS outside. Okay, and then it's also very natural to consider the fundamental period. So what are the minimum elements here is just the elements where S is 1. So for each I, we take pi u. So now necessarily u is a unitary group of signature n minus 1, 1. So if we take pi u with label I, and we define this fundamental period qi pi, so it's again the big pi, to be this q pi u. Maybe I just write, I will write this u1 pi I. So u1 is a unitary group of signature n minus 1, 1. So it will be qi pi u1. Okay, and then it's then very natural to consider our conjecture here. So say another conjecture. So for pi u, as before, we would expect that this q pi u is equal to the product of I in the label of pi u and this qi pi. Okay, so this is our expectation. And later I will explain why we expect this. So if you look at the motivic part, everything is very clear here. Okay. So, okay. So now we have this conjecture, and we can try to prove it. So maybe I want to explain this motivic explanation right now. we first look at this unitary group case, and then we talk about the Shimura case. So if you assume the Laurent's correspondence, we would expect our big pi, which is the classical representation of GRN we expect it to be associated with a motive of rank n, motive over k of rank n. And actually, in this case, this motive is constructed, so the realizations are constructed in my paper with Harold and group, no? With Harris and group. So, okay, in particular, we have this realization, the Betti realization, with this fixed embedding k into C, so it will be a n-dimensional vector space over a number field, I say E pi. Okay, and we have this deRham realization. It will be a rank n free k tensor E pi motive. And we have this comparison isomorphism from the Betti realization to the deRham realization. So again, we consider the fixed embedding here. And we fix an E pi basis of MB and k tensor E pi basis of MDR. Then this automorphic period here, so Qi, they say Qi pi is almost the eigenvalues of this I infinity. It's not really true, but that's something like that. And so here, remember that this Qi pi that comes from, so that comes from unitary group of signature n minus 1, 1. Okay. And then if you look at a unitary group of signature n minus s, so say.
What do you mean by eigenvalues?
You fixed a basis, and then you have a matrix. Then you have these eigenvalues of this, or you have the linear morphism. Okay, but I mean, this is not exactly the cases, because we have another component isomorphism depending on the other embedding of k in C, and actually they are somehow the ratio of two eigenvalues corresponding to the complex conjugation. Okay. Okay. So so now if you look at this base change to pi u, and then now you consider the signature to be n minus ss. And then, so attached to this unitary group, you will get actually the S exterior product of this motif. Okay, and then this Q, say Q pi u, when this I pi u runs over all the possible labels. Okay, and will be the eigenvalues of this S exterior product of I infinity. So then, of course, it's very natural to expect this one as S product of S fundamental periods here, okay, because this is exterior S exterior product. So this is the motivic explanation. And so, for example, if you look at the Galois representation attached to this automorphic representations, then it should be clear. And for
eigenvalues, do you just mean the determinant of I infinity?
No, it's eigenvalues.
But then then you're saying that a number is equal to a set. So I'm not quite sure what this is supposed to mean.
Sorry, I mean the so this when I runs over 1 to n, so it has n eigenvalues. It's a rank n matrix.
But it depends on choices.
No, it does not depend on the choice one. Right. So you should fix, if you want to make it more precise, you should consider the Hodge decomposition of this thing, and you can fix some basis which is very good with respect to each Hodge type, and then you can have this equality. Okay. But if
I'm puzzled because you're privileging an I in this I infinity. You're privileging a specific complex complex embedding. But on the other hand, you're saying down there you're seeing all of them.
So what's that? Right? I don't.
The definition of I infinity is privileging a specific embedding of f into the reals.
Into k, into you mean?
K
Yeah. So that's true. So just as I said to Pierre, so actually you will have another embedding depending another comparison isomorphism for the complex conjugation of this embedding, and you will have another set of eigenvalues, and this QI pi is actually the ratio of corresponding eigenvalues, but I don't want to make it too precise.
I think David's question is actually, is K a CM field or an imaginary quadratic?
Imaginary quadratic field as I assume in the yeah, it can be CM in general, and then you can imagine there will be a bunch of notations then.
Okay, you're already presenting the imaginary quadratic case.
Do you have complex embedding of E pi or not also?
No, it so yes, it depends on the embedding of E pi into Q bar. Of course, I said everything is only true up to algebraic multiples.
All these are E pi, take values in E pi tend to C.
E pi in C or not? There is embedding of E pi to C in this formula?
Yeah, so that's another subtle point. So yes, so eventually everything is actually up to E pi tensor C cross. That's true. But then I should include the complex Galois conjugation of our representation pi. So actually for each pi, so for each sigma in out C, we can construct the conjugation of pi. Pi sigma is another automorphic representation of GRN, and we should consider everything as a family, as an out C family there. And so every result I've written here is Galois equivariant. Okay. So maybe I can write a little bit more. So yeah, that's the point. So for each sigma in out C, so actually this Q is a QI pi sigma only depends on sigma restrict to the rationality field of pi. And then we can consider this QI pi sigma, where so we consider all the embedding of E pi to C, and we consider this family as a number in E pi tensor C. And every relation there is true up to E pi. Up to you have embedding of E pi inside this E pi tensor C, and every result is true up to E pi cross multiplication. Okay. Yeah. So that's in this original conjecture of the linear. So his pairs is inside E tensor C cross. So it's like that. Yeah. So I want to now how much time? So now I want to give the motive explanation for this conjecture of Shimura. This situation is a little bit more complicated, as we have this F is totally real, not only quadratic imaginary.
Actually, here is a question from outsider. Are the monomial relations of Shimura a special case of this?
No. So you will see.
The values of the Galois function.
For the values of Galois function? Sorry, I don't know that. Okay. You mean this conjecture or this? I mean this unitary?
Yes, the one on relations between the fields.
You mean on this unitary group case? So actually, this I mean the L values of Galois representations. So we can read that maybe a little bit from the proof. So maybe we shall see in a moment. And actually, if you we can relate these periods directly with L values if this representation is holomorphic, but otherwise they cannot be related directly to the L values. But in the proof, we shall see when we consider the embedding of a smaller unitary group into a large unitary group, then the ratio of these periods are related to L values. So the parallel situation. So now F is totally real. So now our pi again should be expected to related to a motif over F. Again, so with coefficient in E pi. So for any, now it comes the embedding of F, or real embeddings. So we have M sigma Betti realization is finite dimensional vector space over E I. And this MDR is again the free rank, so rank 2 E pi times the F module. Okay, and we have this comparison isomorphism. So we consider in the sense of the linear conjecture, consider the restriction from F to Q of M. So previously we should also consider the restriction of M to Q, but sorry for I didn't make it precise. And then we have this comparison isomorphism. So where the okay, let's put it a little bit. Where the Betti realization of the restriction, so say MB restriction of M, the Betti realization is the direct sum of all M sigma tensor C. Into the restriction. So the deRham realization is still unchanged when restrict to Q. And you should have MDR. And this one is equal to the direct sum of sigma. So you tensor MDR with respect to this embedding sigma. And then you have this comparison isomorphism. And in this case, this, let's say, we have this determinant, so I call it I infinite. So for each component, there is a comparison isomorphism from M sigma tensor C to MDR tensor sigma C. So it's decomposed as I infinity, direct sum of I infinity sigma. And the Shimura's conjecture is actually something like this determinant I infinity is the product of determinant I infinity sigma. So Shimura's conjecture is about how we decompose a period into embeddings of local periods, but this one is something a little bit different. So the conjectures look the same, but the philosophy behind are quite different. Okay, so I have 20 minutes for the proof, so it's good. Is there any questions? Okay. Now I talk about the proof.
The other big difference between these two situations is that in the Shimura's case, all of these dimension spaces are Shimura varieties, for all the possible, all the different forms of infinity. Whereas in this case, it's only the one signature minus one.
Yeah, that's true.
Yeah. So there's no real motivic. Yeah, I mean, it wouldn't be the conjecture is not a consequence of the take.
Yeah, no, of course not. So yeah, we expect This one only after looking at the Galois representation. Okay. But we cannot really construct a motive from here.
Is there maybe a more refined conjecture where you take into account not just the determinants of the I infinity at each real place, but the eigenvalues of complex conjugation? So the motivic periods in the sense of deLink.
I don't know that because I mean, so in general we have, for example, the Yoshida's construction on some fundamental periods, and we expect every algebraic operators, then this determinant can be written to the products of fundamental periods.
Indeed, I mean that's kind of my question. I think in the unitary case, your periods are Yoshida's fundamental periods, whereas in the totally real case, your periods are somehow less fundamental than.
Right. So yeah.
And I'm wondering if one can extend it that way.
Yeah, I think once given a concrete case, then maybe we can do something. But in general, I don't know, because essentially, if you can write down even every coefficient of this composite isomorphism, of course you can have everything, But I mean, this might be something between this most fundamental and then the general case. Okay. I think there should be a hook somewhere, but
it's on the other.
Okay, I see. Thanks. So the proof. Now I come to part 2. So it's very hard to relate these periods directly because they are on different unitary groups and there are no direct relations among these unitary groups, but we know that there are relations between unitary groups and smaller unitary group of codimension 1, so we shall prove this by induction on N.
So may I just ask you a really stupid question? Is the theorem that the conjecture is true?
Yes, theorem. Okay, thanks. Okay, but it's in progress. But means that I have not really written down everything. But and the conditional proof. So the theorem conjecture is true, assuming. Yeah, assuming certain Archimedean integral is algebraic. So this is something that there are some mathematicians working on, so we would expect this condition can be removed in the near future. Okay. But let me say the proof is induction on N. So we look at V prime, so maybe I continue this way. So you look at V prime in V, a non-degenerate dimension 1 unitary group, Hermitian space, and we consider the unitary group attached to V prime, so it will be a subgroup of U. Okay, and so for any pi, an automorphic representation here and pi prime, so they're both automorphic representations. they are tempered and square integrable case below. So as we assumed before, and then we take an f here, f prime here, and f here. For general f and f prime, no matter they are algebraic or not, we define this GGP period. So the GGP conjectures and also the refined GGP conjecture, the Shimura conjecture, determines the restriction of representation pi to V prime. And more precisely, it gives relations among the L functions and the GGP periods. So, Gangour's Prasad. So originally, it was the question when you have a representation on this larger group one. So what about the restriction to V prime? And we found out that some restriction is contains some pi prime if and only if some L value is non-zero. And then the refined thing give precise prediction about this GGP period and with these L values. Okay. So what is the GGP period? So PF F prime. So we look at the integral of f and f prime. So there's a canonical pairing here. So u prime at q over u prime q. And we normalize it by the Petersson unit product of f and f prime. And you see in particular, if this f or f prime is algebraic, and this one is just the periods we want in the denominator. And so this refined GGP conjecture says, I need more space here. So. So refined GGP. In this case, it's the Shimura conjecture. Oh, sorry, I should mention Neil Harris. So he did that for this unitary case. Then Ikeda did that for orthogonal case. So which says that this PF F prime is equal to, so up to some simple factors, like some power of 2 pi I and some special value of the Dedekind function, and the Archimedean factor I have assumed to be algebraic. And some L values. So the L value here is 1/2 of pi prime tensor pi. So here it's pi, so pi is best change of small pi, and pi prime is best change of small pi prime. And the ratio is this L 1 pi, the SL function. I don't really want to define these L functions, but okay. Prime. Okay, so I have this one. And this work was proved by, firstly, I want to mention that people Wei Zhang and Hang Xue and Bazar basis. And finally, complete form by Bazar basis and Chaudoir. Lidor. So now we have this explicit equality. And then, so recall this is this one over f and f prime. So the key proposition here is that whenever this n is not in the label of pi, for some technical reasons, we can construct for fixed pi prime, for fixed pi, we can construct a small pi prime, and also we should fix the signature of the unitary group U prime such that this one is algebraic and non-zero. So the algebraic are for f and f prime algebraic. Okay. So here, in this case, the algebraicity comes from that for when the signature of u and u prime and the label of pi and pi prime match very well, and this integral can be interpreted in terms of of cup product of cohomological classes. So they should be algebraic. And then, so in this case, this will be some algebraic number over q pi prime u, q pi u and q pi prime u prime. Okay, so this is the basis of our induction. And then on this part, I also only want to mention some names. So based I should always write down the name of Blasius. So to relate these, so there are critical values with automorphic periods. And then the work of Michael Harris and work of Lucio Gerberhoff and Harold Grobner. I say Grobner and myself, and also some important work of Regular. And also a lot of collaborations among these people. I will not write down every collaboration, but maybe here, 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 and here. some collaboration like that. And finally, we can, after long calculation, we can relate this part, these L values, with our fundamental periods. Okay, and then we can finally just conclude by induction. And here, so if you notice that we have a small assumption here, but we can remove this assumption by consider the complex conjugation. Okay, so finally we can conclude by induction and complex conjugation. So now I have 6 minutes. I can explain the one last thing. So I say it's a motivic or an explanation, motivation, application. So this comes from a question that Michael asked me. So he wants to know when this integral of f and f prime can be interpreted as cup product of cohomological classes. So to decide when this one can be interpreted as cup product of cohomological classes. So if this is true, so this will firstly imply that this one is algebraic. And this will imply that. So if you look at the Harris conjecture there, the new Harris conjecture here. So I will call this one, this ratio of L values, I say L, pi prime. Okay, so, and if this is true, then the product of this L pi prime, I don't know why I use this L, times Q pi prime is algebraic. Okay? Or in other words, if this one is not algebraic, then this one cannot be interpreted as cut products. Okay? So from the previous calculation, we can give some. Let me give an example to see what this look like. So of course the simplest one is this one. So we take U1 and U1 prime. So maybe just U1 prime. So signature n minus 2, 1. Signature n minus 1, 1. And we take, I call pi p for any p from 0 to n, such that its label is U1. Just we remove p, so it's here it's AP. And I look at the descending of this pi prime with pi prime q U1 prime. It's just some label like big one. So we look at the case where this is A1. Let's say we look at the case where A1. And so originally we have relations like that. Therefore, each pattern we have different results. And then we have this L pi prime, this Q pi prime. So after the calculation on the right here, it will become this P1 pi Pn minus Q pi to P1 pi Pp pi, and similar terms for pi prime. So we will expect that so this one is not algebraic if n minus q is not p. Okay, so firstly, if this can be interpreted as cut product, then this should be algebraic for any pi and pi prime, and we expect this pi pi to be transcendental as much as possible. And then we see that if n minus q is not p, then this one should not be algebraic. So we can expect this from this calculation. And in particular, we give a precise list of the patterns of pi and pi prime such that this one is not algebraic. And luckily, in the complement of these cases and in the other cases, there are joint work of Michael Harris and Kobayashi and Spey. So let's say the theorem. In some cases, this f prime is cut product. And exactly after this calculation, we show that in the other cases. Then this joint work of Harris, Kobayashi, and Spey. So in the other cases, we expect that this one should not be algebraic, and then we know that these are all the cases we should be able to prove so far. Okay. Sorry, I'm 1 minute over time, so thank you for your attention.
So are there any further questions?
I had a stupid question because I'm complete layman and all of the past went in my head. Is there any relation with this story and the Lin conjecture, on periods?
Yeah.
You briefly alluded to that, but it's of course it's well known. So quickly.
No, it's not. That's not. As I said,
Does it shed some light on the conjecture?
Not as on the conjecture of the linear. So actually, we have already proved the linear conjecture in this setting as much as possible. I mean, so this is some like further work after we proved the linear conjecture. Yeah. So in a joint paper with Harvard and
you assume the Lin conjecture to be true, and then you.
No, yeah. So we proved the Lin conjecture for this motif attached to pi under the hypothesis. So I forgot to say, we also need to assume this certain Archimedes integral is algebraic. And we have another assumption: is certain central L value is not 0, because we use L values as some intermediate term to decide the linear periods. But if these L values are 0, then we get nothing. So the precise hypothesis we need for the linear conjecture is that. So hypothesis for any, let's say, an integer, there exists character chi. So I always in this quadratic imaginary case of infinity type, such with, let's say, with chi infinity to za, z bar minus a, such that this L value is non-zero. So this is our hypothesis, and under this hypothesis and the certain Archimedes integral is algebraic, then we can show the linear conjecture for this motif M. And this automorphic representation. Yes, exactly. And in particular, we can decide, as I said, every L values there, they are critical values. So yeah, this is something really behind this whole work. So I'm trying to hide it in my talk.
You mean for any or for some?
For, I mean...
There exists or for all?
For... There exists, that's enough.
There exists?
Yeah, and character chi, yeah.
There exists some A or?
For any A. For any A, there exists a character chi. Yeah, or for... well, for certain cases, you only need finitely many A, just depends on this infinity type, yeah. And this is of course, very difficult, and we don't know how to prove it.
Any other questions? Okay, thank you very much.